great to be back in Dublin. I've spent many a happy time here, and I see a lot of very familiar faces. So Edinburgh is a great city, but it's not Ireland. So Chris made a historical note, and of course Robert Mallet was educated here. He registered for his degree at the ripe old age of 16, graduated at 20, was elected Fellow of the Royal Irish Academy at 22. Clever guy. And the thing for which he's most famous and most relevant for this talk is his work, which he did following the 1857 Neapolitan earthquake, which killed more than 11,000 people. And he published a 2-volume work on that a few years later. He was given a grant of 150 quid by the Royal Society on the back of letters from Charles Lyell and Charles Darwin to go and do the fieldwork for this book. That's money well spent. And I didn't realise Ryanair were flying in those days, but obviously they were. He ended up working for the arms industry, so I'm not going to dedicate the lecture to him, but I really am struck by the historical relevance of this. This is a list of the 5 biggest killer earthquakes in history ever. We know that there were population densities were so low before this that there couldn't have been any bigger. But one of the really disturbing things about this is you'll see that 3 of these earthquakes have happened in my lifetime, out of all of human history. And we know that earthquakes have killed almost 1 million people in this century alone. So clearly, earthquakes and the study of earthquakes and attempts to try and understand them so we can better protect people from them is a really significant endeavour. It's one I've been working on for a while, and I'm lucky enough to be working with some fantastic people. And I'll tell you something about the work I have done. Some of you have heard me talking before, will be fed up listening to some of this stuff, but I still enjoy talking about it. So we know more than people understood in Mallet's time. We understand plate tectonics, and we understand the way plates move against each other to generate earthquakes. I'm going to talk mostly about these subduction zone earthquakes, but before we start looking at those, we're going to look at some more simpler, just to try and set the scene. So we go to the San Andreas Fault, where the Pacific and North American plates are grinding beside each other. This is the simplest form of fault. It's a vertical strike-slip fault. And I want you to think about the process that happens. Stress builds up as the plates move against each other and they're locked. And somewhere on the fault plane, the strength is exceeded by the value of that stress, and a rupture starts. As far as we know, this is like the size of a 5-pence piece. Okay? Once that starts slipping, it immediately transfers stress to the area around it. So the area around it has to carry the load that was formerly carried on that, and the resultant stress concentration means that the rupture spreads outwards. Now, one very good way of thinking about this is if we have a place in which you have that rupture will continue to spread out until it hits something that stops it. Okay? And if you have a smooth fault, then that would continue forever. But here is a very famous place on the San Andreas Fault, the Parkfield segment. And here the fault is creeping, and here the fault is creeping, so it's not accumulating any stress. So when the rupture hits that part that's really slack, it can't drive the earthquake through it, and the earthquakes tend to stop top and bottom of this. So what we get is a place that actually breaks as though it were one segment. Okay, and we get the idea of a fault segment, and we can model that sort of mentally by a block with a spring attached to it, and then we can start thinking about what happens whenever we build up the stress. And you can see that the stress with time, as the the plates move against each other and the fault is locked until the stress on the base of this exceeds the friction, and then we get a sliding event like an earthquake. Then from that relaxed state, we start building up again, and again we get to a state where the stress is bigger than the strength, and we get another earthquake. And you end up with events that are uniformly spaced in time, so you know you're going to have another one here and another one here, and of approximately the same size. These are called characteristic earthquakes. And when we look at what actually happens in Parkfield, there is a lot of evidence that maybe that's actually happening. So if we look at seismograms recorded in a very old station somewhere in that region, I couldn't tell you exactly where, you can see that in 1922, this seismometer recorded that seismogram. In 1934, it recorded this. These seismograms are remarkably similar. In other words, it looks as if the same earthquake is happening. And when we plot the event number in the sequence against time, you end up with this. And this famous paper by two guys called Backhun and McCloskey led us to believe that the seventh earthquake in this sequence would happen in 1993. And the result is the US government spent $500 million putting equipment around that site to try and catch this big earthquake happening. And it didn't happen in 1993, so this one was about 10 years early. So they're 22-year sequence here. This one's about 10 years early. This one, the next one was in 2004, so it's over here somewhere. It was about 10 years late. But the idea is that this looks like a repeating pattern for earthquakes. And now we're going to move to, having thought about that, the San Andreas, one of the most studied faults in the world, of course. They've got plenty of money. They've got lots of equipment around it. The 1906 earthquake in San Francisco meant that there was a lot of interest, and the result is we've got fantastic amount of information. So people take these ideas that appear to work here and move them to somewhere else, and that brings me to Sumatra and Nepal, where I'm going to talk about for most of the rest of the talk. Chris, do you know when I started? Quarter to, okay. I'm ahead of time. That's not, those people who know me will know that's the first time ever. Okay, so we're interested in the subduction here. So we've got the Indian plate is being thrust under the Himalayas here, and we're interested in the Indian and Australian plate. I'm not going to go into the details of the tectonics, but basically you've got convergence between the Sunda block here and these oceanic plates, and you've got subduction along there. A fantastic piece of work, which is actually based on the work of Mallet, the idea of mapping isoseismal lines. And Newcomb and McCann took historical records along here and mapped out the extent of some very big earthquakes that happened along the Sumatran megathrust. And this is what you get. So here's the ocean plate, and it's being forced under this. And the question under Sumatra, and the question is, given this sequence and given our ideas about how earthquakes repeat, what's going to happen next? Let's see why this is a very important question. Here, I'm not going to discuss these graphs at the top there to do with the way, measurements of the way the plate deforms. But this is a simple picture where the oceanic plate is being forced onto the continental plate, and you'll see in Sumatra there are a row of islands here, and they become part of the story later on. So you can see the island here, and this plate's being forced under. So immediately after an earthquake, everything's relaxed like this. Then the stress builds up over the next 100 years or so, until it gets to a stage where this locked section is loaded so much that it can't take any more stress. Somewhere 20, 30 kilometers below the surface, one small part, this size, breaks, and a rupture starts propagating outwards. Okay. What happens then is that all the strain energy which is accumulated in here is released, and the fact that this island has now been pushed under the the sea by the deformation is completely recovered really quickly. Okay, so that's maybe 100, 200 years of strain accumulation, and all of this is happening in a few minutes, depends on the size of the earthquake. But all that energy is released in a few minutes. This isn't, we can actually see this happening. So an earthquake I'm going to talk about later that happened in 2005, this was what the south of Nias Island, one of these islands, I'm not going to the geography, the south tip of that island looked like that before the 2005 earthquake, and you can see this banana plantation, which was a few hundred years ago was producing bananas, was pushed onto the sea, all the trees died, and after the 2005 earthquake you can see the banana plantations back in business again, and people who don't know about plate tectonics might start planting out their bananas again, and they would get 100 years before they were put out of business again by another earthquake. Of course, that movement of an island up through the water column produces a wave, and that wave propagates outwards, and of course it steepens as it comes to the coast, and produces a tsunami, which can do an enormous amount of damage and kill a lot of people. Okay, why is it particularly important in Sumatra? Well, one of the reasons is this whole coastline is very densely populated, and in particular the city of Padang has a population of just under 1 million, or it had a few years ago. I'm sure it's over 1 million now. And those, almost all of the 1 million people live at below 10 meters above sea level. So a tsunami striking this city from one of these earthquakes here, particularly in this area, people have estimated that the expected death toll would be in the order of 500,000. So this would move it up into one of the worst earthquakes of all time, should this happen. So clearly a lot of people were very interested in this, and many people were asking, what's going to happen next? Well, on 8:30 in the morning of Boxing Day in 2004, a place just under, 30 kilometers below the surface here broke. A rupture started, and it started propagating outwards. For comparison, this is just about here. Notice this is the 1861 earthquake happened in this region, stopping at Simalu Island, but rupturing all of under Nias Island. So I'll come back and mention these before. We're now just starting here, and the rupture didn't propagate southwards. So even though it started just north of the 1861 rupture, it didn't propagate southwards, it propagated unilaterally northwards. And we ended up moving the seafloor the way it was shown you. And here's a simulation of what happened in the next 10 minutes. That the seafloor moved up to 6 meters vertically, and the end result is that we ended up with about 1 trillion tons of water displaced vertically above. Incidentally, the length of the rupture along here is about 1,200 kilometers, magnitude 9.2 earthquake, second biggest earthquake ever still. Okay, so this was a mammoth event. And this was a simulation which didn't capture the full length of the rupture. We know a bit more about the earthquake since then, by Eric Geis from USGS. And what happens, that bulge in the surface of the water, obviously vertically exaggerated here, collapses, and the result is, notice the way the waves steepen when they go into shallow water. This isn't just a splash that you get in a bath, it's a conservation of energy effect. And the maximum wave height here was over 50 meters. 50 meters high. So imagine that striking a city like Padang. The survivability is very, very low. And the wave propagates outwards, struck the coast of India 2-3 hours later, and it was still killing people 10 hours later along the east coast of Africa. This was a real shock for me, because I thought scientists were doing a good job in communicating stuff. All these people, there were certainly 80,000 people killed in Sri Lanka and India, well within the range of a warning had people been organised to give them that warning. So 80 or 90,000 people, hundreds of people, maybe 1,000 in total along East Africa were killed by this. So I was quite shocked that even in this day and age, we weren't communicating science well enough. Okay. Banda Aceh is a city of something like 150,000 people on the northern tip of Sumatra. This is what downtown Banda Aceh looked like, the harbour area before the earthquake and after the tsunami passed. I don't like showing graphic photographs of damage, but this is a real, there are thousands of hours of video online that you can watch the devastation of these tsunamis now. The wave, the total death toll was in the order of 225, 230,000. Nobody really knows the final number. Okay, how are we doing with the characteristic earthquake, this idea? Well, we have an earthquake here which stopped somewhere here, so it looks like the characteristic earthquake would suggest that this is a barrier, something that's stopping the rupture from propagating northwards. Now we have this 9.2 earthquake which stopped at around the same place. So it looks as if it can't propagate southwards. So this is the type of thing you expect. Of course, we wouldn't have expected something to rupture the whole way up here. You would expect something maybe the same size as this, but at least at the minute this is looking okay. So what's going to happen next? Well, at the time of this earthquake, we had been working on calculating stresses around earthquakes with a view to trying to understand earthquake communication and aftershocks in particular. Okay. So when an earthquake happens, it actually bends and twists the rock in the surrounding area, and that makes other earthquakes either more likely to happen, depending on where they are, or less likely to happen, and we can calculate what those stresses are and produce maps of the change in stress. Good example of this is work that we did, derivative slightly of work done by Ross Stein and Jeff King and others, on the Landers earthquake. Here's the stress map around the Landers rupture, which ruptured these three faults. And here's where the aftershocks ended up. And you can see they're very well mapped out by the red areas. So I was on holiday in Donegal on Boxing Day in 2004, and the local radio station phoned me and said, "John, there's a big earthquake and a tsunami. Do you know anything about it?" And I got access to internet, saw what had happened, and immediately phoned round my research group, and we were in the university the next day, and we calculated what the stresses were as a result of that earthquake, and we published this paper in Nature. We submitted it on the 10th of January 2005, first paper that I know of that was published on the 2004 earthquake. It took them 3 months to review it, and one of the reviews was longer than the paper. So they do take it seriously. It was published almost without change, so we were able to answer those things. And it basically suggested, among other things, that there could be another large earthquake here, and if the characteristic earthquake was right, the hypothesis was right, then we would expect it to be around magnitude 8.5. And notice this is St. Patrick's Day when the paper came out, and 11 days later, a magnitude 8.7 earthquake nucleated there. That's the 2005 Nias earthquake, and we had it in Nature 11 days before. I was ill recently, and the doctor said to me, being funny, "What's your favourite earthquake?" And I went, "The 2005 Nias earthquake." As you can imagine. Anyway, to try to put this in context, how amazing that is. I was interviewed this afternoon on News Talk Radio, I think you call it. And the first question he asked me was a cracker. He says, "Why can't you predict earthquakes?" Barry, shake hands. That is the way I would shake hands with you normally. Here's a very limp sort of shake. That's the amount of stress that there was at this point. 30 kilometers below the surface, the stress in a very meek handshake was enough to trigger the fourth biggest earthquake ever recorded at that time. So you can see why, and what I said to the guy this afternoon was, stress of a handshake 30 kilometers below the surface causes a massive earthquake. And how are we going to predict that? Okay, so incidentally, the blue patch here now is the magnitude 8.7 2005 earthquake, and you'll notice it stops at about the same place as the 1861 earthquake. Turns out that there's a fracture zone being subducted just here, and it looks like the smoking gun for why the earthquakes are stopping there. So this looks good for the characteristic earthquake model for the earthquake in Sumatra. So what's going to happen next? Well, no prizes for guessing what we did. We calculated the stresses in this area, and we published another paper in Nature 3 months after the first one, saying that now we're really looking, Padang City's just here, so we're now looking at the 1797 earthquake zone being about to break again. So it's this area, really dangerous. We know that since 1797, there's probably 15 meters of unresolved slip stored on the fault, because we know the speed of convergence of these plates. And there was then a flurry of activity between our group, the Caltech group. There were groups from Germany, obviously a lot of Indonesian scientists were working on this. And we looked at what types of tsunamis could be caused from a whole variety of different earthquakes. We tried to focus on Padang to see, and we saw that, the same magnitude can produce completely harmless tsunamis, or ones that will kill 1 million people, well, 500,000 people. We found that no matter what size the earthquake was, the timing, it always arrived about 25 minutes after the earthquake. The tsunami arrived on the shore. And we put all of this together. I'll not go into details. Some really high resolution work done by the German team allowed us to see exactly the way there would be inundation. And the result was that this is Kerry C from Caltech. A lot of us were interacting with the local government there and helping them to try and make sense of the complex results that we got from our simulations. And we produced evacuation maps. Well, we didn't, but we advised on the right values. So red, yellow, green, below 5 meters, between 5 and 10 meters. The simulations would have suggested that mostly above 10 meters. We did evacuations in schools, so I did a lot of going out and talking to kids in schools and then helping them to walk up, or walking with them up hills and stuff. It was interesting. It's quite disturbing because you knew that they had about a half an hour, and they were all doing exactly what they were supposed to, and we got to the safe place, and you looked at your watch at 1.5 hours after the earthquake. We were suggesting, lots of us, that we should build vertical evacuation structures in the city. We reckoned that had they done it, we could have saved 100,000 lives, and the cost would have been about 2 million. And they didn't do it. So we reckon, some people calculated that meant that the value of a life in Padang was less than $20. I know that's it's not a very clean way, or it's not a very clear relationship, but nonetheless the math works. So what's going to happen next? So this is the situation now in 2007, and of course we're going to get an earthquake breaking here. That's what happened. Okay. 12 hours later, that happened. 2 years later, an earthquake just here, 50 kilometers below the surface, nothing to do with the plate interface at all, something we weren't expecting, happened. It killed 1,200 people in Padang, and everybody in Padang did exactly what we had been trying to tell them not to do. They all tried to cross one bridge. There were 200,000 people trying to cross one bridge. They would have been all killed, for sure. It turns out that this wasn't the earthquake we're expecting, and as you'll see, that earthquake hasn't happened yet. 2010, we had another earthquake here, and whenever you actually get down and look at it, instead of just these big earthquakes above magnitude 8, you actually find that there have been 30 or 40, I think there's 35 earthquakes in this picture, above magnitude 7. And if you take a catalogue for this area, so an instrumental catalogue for the last 30 years, that's what you get. So the idea that earthquakes are just characteristic is obviously completely wrong. And yet it seems as though It gave us a good steer on what was going to happen in 2005, gets everything completely wrong after that. So the end result is that we now have a situation where you've got earthquakes happening at all scales, and they're being triggered by tiny amounts of stress, and your idea of deterministically trying to work out what's going to happen next is just all bets are off. So a lot of us at that time were trying to think of other ways of approaching this problem. And people in the physics community were thinking about something completely different. The behavior of multi-component systems that were being driven and that energy was being drained out of them somehow. The classic paradigm is this idea of a sand pile. Okay? So whenever you add grains of sand to a sand pile, the pile gets steeper and steeper and steeper, and you start getting avalanches, and then the avalanches can be very small, and you get lots of those, or else they can be sometimes really big. Let me see if I can get this to work. So this is an experiment. I better put my glasses on, I'll push the wrong button and everything will go crazy. Why does it always work when you're practicing? Okay, so here's it. Incidentally, the sand pile experiment doesn't work with the sand pile, you have to use rest. But anyway, you can see that we did a version of this experiment far better, because we didn't just pour the grains on like that, we put them on one at a time. And the end of the day is you get very small avalanches happening all the time, and I'm pointing with my glasses, not very effective for people, and then you get these big events. And it turns out, when you look at that, I better just stop that. When you look at the way the events happen there, you end up with a sequence of events that look like this, very raggedy, some big events and lots of small ones, and then tiny changes. By putting on one grain of rice, you can end up making the whole pile collapse. So you end up with this very importantly, when you plot some measure of the number of avalanches against some measure of their size, you end up with this power law distribution. So you get a straight line here in this roll-log space. Okay? These roll-offs are to do with the system size. Okay. So when we look at earthquakes, it turns out you get exactly the same pattern. So this is magnitude. Don't worry about the nature of the scale, it's basically magnitude. This is basically the log of the number. Okay? And you can see this is for the Harvard centroid moment tensor catalog for about 60 years, all the earthquakes. Incidentally, this is before the 2004 Sumatra earthquake, and this is after. So we published this paper in Nature Geoscience at that time. We knew the size of the biggest earthquake the planet could have in 2003, and we didn't know it in 2004. I think that's really sweet. But anyway, fortunately, the editor of Nature Geoscience also thought it was quite amusing. When you look at this power law relationship as the Gutenberg and Richter law, it's the same everywhere. And if you do your statistics properly, the uncertainty trumpets out like this, and the end result is that even the magnitude 9 in Sumatra is actually not unusual given the observation of small earthquakes. So this, and even if you go to Parkfield, the poster boy of characteristic earthquakes is Parkfield, and that's the 6s that we get at Parkfield. Dave Jackson and Jan Kagan pointed out that they were exactly what you'd expect if you just look at the small earthquakes. So we now end up with, why is it that these big earthquakes look as though, in Sumatra for example, look as though they're special? Well, the thing is we're just ignoring all the small ones. If you get rid of those, you start seeing these big things that are recorded in the record, and they start looking more periodic. Especially if you put your periodic glasses on, then immediately everything looks to conform to that idea. And the end result is that this is a power law distribution And if you sample it badly, you end up with things that start looking more periodic. Okay, so where are we? Chris, I'm a half an hour in. It's not too bad, I don't think. Okay, so where are we? This characteristic earthquake, there are places where it might be a good way forward, but in general it doesn't work very well. And you've got a situation where tiny stress changes happening impossibly deeply below the surface for any deterministic measurement of them can produce very large earthquakes. The earthquakes have all possible sizes, but one thing we do see is, Dave Jackson said to me, he said, take a 100-kilometre hoopla hoop and throw it onto the earth anywhere where there's earthquakes and plot the size distribution, and it's always the same. When you're looking at earthquakes generated by fracking, they have exactly the same distribution. There are a couple of volcanic cases where whenever you do things a very special way, that relationship breaks down. But apart from that, this is one of the strongest relationships in seismology. We might be able to use that. During the 2004 earthquake and what followed, I got friendly and started working with a guy called Dominic Crowley, who's the head of the emergency unit in Concern Worldwide. On the 12th of January 2010, again down 20 kilometres, well in this case 15 kilometres below the surface, something that size broke, ruptured, earthquake on the Plantain Garden Fault, slipped a metre or two, magnitude 7, killed, the Haitian government estimated 300,000 people killed. 3 days later, I remember it well, I was drinking coffee in my kitchen in Donegal, and the phone rang, and it was Dominic Crowley from Concern, and I said, how you doing, Dominic? What's happening? He said, I'm in Haiti. Okay, so while I was having coffee at home, he was out trying to help people in Haiti. Fantastic organisation, Concern. And he asked me, he told me what was happening, and that there were a lot of their staff were leaving because aftershocks were scaring them. And they had to live, they were sleeping in tents outside a hotel, in the garden of a hotel. They had 200 people or something in tents. And he said to me, John, can I move these people into the hotel? It looks okay. And I'm going, shit, I'm an inch, in Donegal. Can I said, okay, Dominic, I told you I would try and help you when these things happened. Maybe we'll do a wee bit of work beforehand, before the next earthquake. But I worked with him over the next week or two, and the people ended up, we got structural engineers and got other geophysicists involved. The place where the hotel was on very solid ground. The people moved in. I didn't sleep for a month, doing that, and I still haven't made up my mind whether I did the right thing or not. At any rate, after that we said, we're going to do this properly if we're going to do it again. So we got money from NERC to start looking at how could we use the science. In this case, it was this stress interaction that I was most interested in. How could we use that forecasting of aftershocks to produce a tool that could be used during emergency response? So this was in about 2012 or 13 we got this funding. And this is one of those times when I discovered something really important, only to find that somebody else had discovered it 20 years before. So this is the Gutenberg-Richter rule. The wee roll-off here is just because you can't see small earthquakes as well as you should. Okay. The other rule, if you locked 5 seismologists in a room and said to them, you're not getting out until you agree the 3 most stable laws in earthquake physics, they would all die of starvation. They would get the Gutenberg-Richter law in the first 30 seconds. They would follow it up within 1 minute by the Omori law, and then they couldn't agree on the next one. So these are the 2 most stable laws. When an earthquake happens, you get a power law decay. I'm not going to do any maths, but basically there's a very well defined decay of the number of events that you get with time. So I thought, if we do this and extend it out a bit and then integrate that and then stick it into this, we'll be able to see how many big earthquakes you expect and the ones that you know you're going to get. Really clever? Let me put that somewhere different. So here's a set of earthquakes. We're now at time T1. We've been looking at these earthquakes. We fit the Omori law to them, and then we use the data in here to work out our Gutenberg-Richter rule, whatever's happening. And we've got two parameters, the A and B here. And the slope of this line gives us B, and we're going to say B will stay the same over the next while. Then we extrapolate here, integrate that area, and that gives us the A value. And now we can say, this earthquake will happen that many times. And this is now a forecast. So it allows me to produce a table of probabilities of an earthquake of a certain size happening in the next 10 days, or 20 days, or 30 days. And we can do that for all earthquakes. And all of that's trivial. But mathematically this is fairly straightforward. What is interesting is you have to now try and understand what 0.42 means to somebody who's living in a tent outside a hotel. And that's a very much more difficult problem. So we ended up trying to work through what these numbers would mean for the standard operating procedures of an emergency response organisation like Concern. And that was interesting, and it was all pretty academic, even though we were trying to be serious. We were still sort of playing games, until the 25th of April 2015, when the Nepal earthquake happened, and immediately Dom Hunt, one of Dominic Crowley, everybody in Concern is called Dominic, don't understand that. Dom Hunt phoned me and he said, I'm on my way to Nepal, we've got this earthquake happening, we're responding to it, we want you to help us now, the way you've been talking about for the last year. So immediately we started thinking about what had happened. Jean-Philippe Avouac, who was in Caltech at that time, he's now in Cambridge, produced this summary of the situation. Here's the earthquake that happened, magnitude 7.8. Here's the earthquakes we've had before. So in 1500 there was an earthquake certainly bigger than magnitude 8. Historical records aren't great, so we're not sure of the extent of it. Here's one in 1934. This is what happened. And immediately people started talking about the partial rupture of the gap between here and here, and raising the prospect of another magnitude 8 earthquake which would rupture this area. Instead of doing that, I said to the guys in Concern, let's just do what we've been practicing. And we started flipping these parallel relationships. So this is actually data that we were working on at the time during the earthquake. And if you take the Omori law and plot it in its cumulative form, instead of doing that, it does this, and it looks like that, and you make a forecast that this is the way the events are going to happen in time over the next while with some uncertainty. And that allows you to use this number, stick it into a line parallel to this, and it allows us to produce these probability tables. We had also thought about, if you look at the activity, so this is a map of the number of earthquakes happening per day, per square kilometre, over the period of time since the event started, you can see that this is the area that's most active. And if you think about the Gutenberg-Richter rule, if you've got more earthquakes, the biggest one's going to be bigger, so this is also an area. I have good fun trying to teach this to undergrads, so some of you are going, I'm not sure about that, but anyway, it turns out that it turns out to be a probability distribution for the earthquakes of different sizes. The probabilities are different for different sizes, but the shape of the field looks the same. So we were putting this stuff out, and in particular, on about day 15 of the sequence, I'm not going to try and work out the exact numbers, we sent this because the UN agencies had come back and said there is going to be a second earthquake based on this characteristic earthquake idea. And people were phoning me and saying, what do they mean a second earthquake? The ground's shaking here all the time with earthquakes. They had experienced 130 magnitude 4 or greater earthquakes in the last 10 days. So the idea of a second earthquake, I said, don't worry about that. This is the deal. you've got about 17% chance of a 7 or bigger, and that, if you take the worst case, given the uncertainty, is probably up to 30%. Don't allow anybody to go back into buildings, even though the total number of earthquakes has dropped off. You're still really dangerous here. Don't allow anybody into buildings, and the people in concern were trying to persuade other NGOs who were starting to allow their staff to go back into buildings. When the magnitude 7.3 Gorka earthquake happened, every pall of smoke here is a house collapsing. I have the concern online have a video of this. They actually were videoing in the area, and this is a snapshot from it. So it gives you some idea of what we're talking about. This earthquake, which happened just here, okay, was something that we were talking about as being 30% likely. It killed another 900 people. Certainly, I don't know of any response people who were killed. Certainly, none of the concerned staff were injured as a result. We've done a lot of analysis on the forecast of this. Incidentally, you see here, this is the second big earthquake, and you can see that the number of aftershocks immediately shoots up in response to the second perturbation. And we've looked at, so when people were being told that the second earthquake had now happened, people were saying in the field that that's it, over. The second earthquake's happened, everybody can relax. Turns out the probability actually went back up again here. So after day 18, when this earthquake happened, the probability went back up in the air. So it was actually as dangerous as it was after about day 2. Okay. So again, how you translate this information is something that we're going to have to work on over a long period of time. But you can see here that the idea is that the science is starting to interface and at least giving people some way forward in dealing with these really unpredictable issues. I got a small grant, which I'm really pleased about, just yesterday, to get together people that we've been working on this. So UNESCO, AFAD, we've been working with them for a while. That's the Disaster Emergency Management Presidency for the Turkish government, Kandili Observatory and BGS, Met Office. ADPC represent they have the Secretariat for about 7 or 8 earthquake-prone countries in Southeast Asia. They have about 1,000 civil society organizations, GNDR, Global Network for Civil Society for Disaster Reduction. They're all going to come to Edinburgh to try and take the next step in learning from what happened in Nepal so that we do that. So it's a small grant, but I think it's designed specifically for impact. And I'm looking forward to that. Okay, how am I for time? I've got about 4 minutes left, I think.
5 minutes.
Oh. John Walsh is going, shit, that's the first time we've heard it. Okay, so I'm going to talk to you, and if anybody asks you about this outside, I didn't say anything, but I can't resist talking about something that we've just had funded in Edinburgh. I've been working, the British government under their Global Challenge Research Fund has been looking for trying to interface research with development for lower and middle income countries. So we have been over the last 18 months putting together a big international team to try and look at disaster risk in tomorrow's cities, not just earthquakes, volcanoes, landslides, floods. This is Quito, one of the cities we're working in. This is Cotopaxi volcano. Isn't it absolutely beautiful? It's just a quintessential volcano. There are there are populations living on these slopes with lahars, avalanches. There's a massive, very active fault along here. This is what some people call a hazard hypermarket. Everything's there, flooding in these low areas. So we're working there, and we're working in other cities. We were asked to look at an intractable challenge, something that people couldn't solve yet, and they're going to give us some money to look at it. 2 billion people are exposed to natural hazards in lower and middle income countries. It's expected to double by 2050 by population growth and marginalisation of people. And cities have 55% of the global population. So if you put all that together, we expect about 2 billion urban dwellers to be threatened by natural hazards in the next 20 or 30 years. On top of that, 60%, this is something I was stunned by, 60% of the area that's expected to be urban in 12 years' time hasn't been built yet. So these are UN figures. Now, clearly, this rapid urbanization is normally seen as a real threat, but on the other hand, it provides an opportunity to try and do something with planners so that they do things better for the next generation of poor people, particularly. It's the poor who always die in these things, and women and children disproportionately. So what we've done is, this is the aim. We're trying to, at the minute, people build whatever they get away with, and then they try and produce some emergency response system that solves their conscience. So instead of using crisis management, we're trying to build risk-informed planning into these cities. We have chosen 4 cities, not just because we like them and we've got networks there, but these cities are actually working to try and do this themselves. And we're able to bring a very significant international scientific and engineering and social science and political science multidisciplinary team to try and help them to do what they're already trying to do. So maybe Chris will get me to come back sometime in a few years and I'll tell you how this is going. Thanks a million for nodding when you were supposed to. Thanks.
Any questions, comments? Peter.
So forecasting any of these kind of things, whether it's solar flares, which is the kind of thing I do, or weather forecast is really difficult. And you can say it's going to be this big in this interval. But do you ever look at skill of how good you are? Do you have a skill score of, or are you good at it? Are you a 1 or are you a 0.5, or are you just random?
Yeah, this is really good, obviously a really good question. You can't just wheel this stuff out and assume. We're pretty good at it. So there are standard, over the last 10 years or so, people have developed measures of forecasted success. The problem is that it's not that difficult to get a good score on something that's already happened. It's very difficult to keep it clean. So I see a lot of papers published where people are prospectively, pseudo-prospectively making forecasts. And actually you can see that the parameters have been tweaked to give them the answer. So keeping that clean is very difficult, but we are taking this seriously, and I think it's pretty good. I can say that we aren't the only people doing this. Rosenberg and Jones came up with this in 1989. There are other groups doing similar things. I think where we're ahead of the field is that we're actually working with the humanitarian organisations to make it happen. So I think it's pretty good. Good question. Not completely convinced.
No, it's a hard one to ratify, yeah.
This one, do you ever get 2 plates subducting together or jammed together? I mean, one plate is nearly always going into the other, but do you ever get
I'm sure some geologists here would say why you don't get that. One of them is always slightly more buoyant than the other, so one always goes underneath. So India and Eurasia, you would think will just do that, and to some extent they do, because the Himalayas thicken up, but eventually one of them goes under the other. Anybody got a better answer? I know I'm looking at some people and they're going, McCloskey's bluffing.
Everybody's looking at the floor.
I think that's the answer. One of them always wins. 25 years.
Yeah, 30 years of the Dublin earthquake. It's quite bad. Do you have any predictions for this one, like this region also?
I don't work there at all, and one of the reasons is because that's really complicated. You know, I'm trying to, in that phase of my life where I was trying to work out, you know, can we say what's going to happen next? I argued that we should always go for the simplest places first. Armenia is really complicated. The North Anatolian and South Anatolian faults come together, and then you've got Armenia behind that taking up all sorts of strain. I know the Spitak earthquake, wasn't it?
It was Gubri like 30 years ago, but even like Gubri earthquake, if I remember, was 30 years ago.
I just heard somebody 2 days ago telling me that that anniversary had come up.
There was also like entire like region, like which is now in Turkey, but like it's very nearby, like Ani earthquake. Which was also
Sure, we've worked quite a bit in Turkey over the last while. So the point is that the Gutenberg-Richter rule that I showed you works in Armenia as well. So if we measure small earthquakes that happen all the time, you can say how likely a bigger earthquake is. Of course, that's a different thing to being able to say something that's useful. So I think once people have built stuff, then it's really difficult to try and make that stuff resilient. Where we're trying to focus on is in the places that haven't been built yet. Can we do better with that? John. Oh, sorry, Chris.
I was wondering whether you can comment about the sort of almost polarised approach between seismologists on one hand and paleoseismologists on the other.
Oh dear.
Where you have the seismologists dealing in 3D and so on, and actually really getting a proper sample of the world. Paleoseismologists are stuck in the trenches. To what extent?
I'll have to remember those.
To what extent do you think paleoseismologists appreciate that maybe the battle won't be won in the trenches, and we need to go away from characteristic, and we need to actually start talking about systems which will be as complicated as they are?
I mean, I think the battle is lost in the trenches, really. You know.
So could you just summarise briefly what a paleoseismologist
Okay, good. Thanks, Chris. Earthquakes don't happen very often. Thankfully, big ones don't happen very often. So rather than being able, if you're not there when it happens, you can go back and dig a trench in the ground and look at the structure, the stratigraphy, for those of you who know geology, and you can see the scars left by earthquakes that happened in the past. And if you use carbon-14 dating, for example, you're able to tell when a particular earthquake happened, plus or minus. The problem is, and I think this is John's point, is that what you end up with is getting a very, very biased sample of what actually happened. Because lots of the time the earthquake doesn't rupture the surface at all, so it's not recorded. So a magnitude 7 earthquake doesn't rupture the surface, you don't think it's happened at all. So the paleoseismologists in Sumatra, for example, have got a great record of earthquakes, you know, and they really, we've worked on inverting from, in this case it's corals that move the seafloor up and down, and the corals actually record exactly, they're like GPS instruments measuring the vertical component of deformation for hundreds of years. And you're able to use the measurements of displacement to actually work out the whole slip distribution on ancient earthquakes. That's fantastic. But the only ones that are recorded by the corals are bigger than magnitude 8. So the end result is that what John's asking is, seismologists, it's an interesting one, seismologists see all the earthquakes down to magnitude 2 in California, for example. Paleoseismologists only see earthquakes down to magnitude 7 in California, for example. The thing is that they see it back for 1,000 years and we only see it for 30 years. So I think that there's a lot to be learned from that community. And the problem is, I think all of us need to do a course in science, because once you understand about sample bias, once you understand about, and have a realistic view on the way your data is actually illuminating the problem, then I think a lot of these problems disappear. At the minute, there is a war. So me and Kerry Sees, we're good friends, we talk a lot, and we really don't agree with anything we say. So.
Okay, so we'll take two more questions.
I know you do a lot of work with concerns, but in general, do you find either the emergency response agencies or even government agencies that you have there, are they open to this kind of work? You know, do you find that you're looking at sort of planning and forward planning? Do you find that they're open to it, or are they not interested because it's not an immediate problem?
The reason why we chose, for example, the cities we've chosen for this new project is because we know that they're interested. So the biggest problem isn't the science, you know. In fact, to some extent, once we get our foot in the door, the science almost disappears. Once you get people conscious of this as a big issue, then engineers can come in and do enough to make the next generation of buildings pretty resilient. The thing is that the social scientists and the political scientists want us with them because nobody will listen to them until they've come in with us. And the end result is that you do really get a way in the door, and in some cities people are really keen, in other places they're not interested. So it's variable.
John, one thing I got from your talk was a move that in terms of useful prediction, a move towards statistics and away from mechanics. I mean, is that an oversimplistic conclusion?
It's not, no. Unfortunately, as somebody who fancied himself as a sort of physicist, we failed on that one at the minute. No, I wouldn't say give up. We have a paper which we're about to submit looking at a physics interpretation of aftershocks. So there are a number of papers being published that say that if you calculate the stress around an earthquake and then do the statistics based on the stress rather than just the statistics, you end up doing better using physics than you do using... The thing is that this is a case where Peter asked me earlier about forecasting. I'm convinced that they actually do that by tweaking the knobs until they get the right answer, and then they say, oh, look at that. So there's some good friends of mine who aren't going to be too pleased about this paper. But when you take in the uncertainty in the forward model, not in a pseudo-prospective model, in the real forward model, you end up, you know almost nothing. So the end result is that at the minute, physics doesn't do as well as statistics. Now, I'm more interested in physics, but when I'm working with concern, they're more interested in getting the right answer. So, and at the minute, we're using statistics.
So in the era of big data, we're going to struggle to find some physicists down the road, I think. We'll all be out of a job.
Well, you know, just to comment on that, it seems to me that if we can get rid of a lot of our old ideas and just look at the data properly, then the physicists have got a whole new job to try and understand the new interpretations that will come out of big data.